Okay. I'm John Whaley. This is Jeffrey Thomas. Today we're going to talk about sandboxing. And so there's been a lot of news and interest in sandboxing recently, for sandboxing for security, and a lot of fact and a lot of fiction. So hopefully we'll be able to help you distinguish between the two. So I'm, who are we? Well, I'm John Whaley. I think this is my 6th time speaking at BriForum. I founded a company called Mocha 5, although this talk has absolutely nothing to do with anything Mocha 5 does. This is just a, personal interest of mine and the sandboxing. So hopefully I can give you an independent view. I have no connection to any of the vendors that I'm going to be talking about or any of the technologies either, just personally interested. I dragged Jeffrey along with me because Jeffrey's a recent MIT grad. A bunch of his work on his master's thesis was on sandboxing. So he's definitely an expert in the area. Again, doesn't have any connection to any of the vendors, so hopefully we can give you an independent view of these things. So sandboxing, there are tons and tons of sandboxes that have popped up. Like you've probably heard a lot of these things, like Bromium. So like Invencia, they just announced this big OEM deal. They're going to OEM and put their stuff on 20 million Dell machines. And there's a number of others that standalone Windows solutions. You may have heard about sandboxing in terms of applications, like Google Chrome has a sandbox built in, and Adobe Reader, things like that. They make appliances that do sandboxing as well. And operating systems are starting to build this technology in to it. So so there's a whole lot of sandboxes out there, and each of them uses a little bit different technology. So hopefully, by the end of the session, we'll be able to understand what the difference is and how to evaluate these. So along with sandboxing comes a lot of hype as well. So you see a lot of these things that. Technology to kill all malware forever, and okay, that one somebody was happened to be talking about Bromium. There's another one, always 100% isolated, eliminated, always protected against all known and unknown attacks, which sounds awesome, Here's another one, like guarantees that all advanced target attacks are defeated. Oops. Oh, I got a meeting notification. Sorry about that. Yeah, Invencia, they got spear phishing problems, use us. Gartner's is on it too. They say, by 2016, 20% of enterprises are going to be using some type of sandboxing or containment mechanism to handle their untrusted code. So Gartner, and there's a lot of hype. I mean, if you guys were in Simon's session where he described how if people don't use these kind of technologies, that society as we know it is over. That's so there's definitely a lot of hype around it. Some of it is true, some of it is justified, some of it is not. So we'll go to that. First of all, what is sandboxing? We're taking a really literal and academic view of it. Sandboxing is really, if you get right down to it, it's using virtualization for isolation. And so when we talk about virtualization, this is not just virtualization like virtual machines, but includes other concepts. This is things like virtual memory, virtual file systems. This is virtualization in the more general term, because a lot of the sandboxing that doesn't necessarily imply a virtual machine. This is really adding a level of indirection so you can isolate the effects of some process or task. This allows you to isolate potentially untrusted code and run it in a separate execution environment or container, and then be able to contain the effects of that code. Yeah, and then that's my clicker is a little flaky. So generally speaking, sandboxing will run unmodified software in the modified environment. So there's some other techniques to basically be able to take a program and basically you can write the program in a certain way so that you can you can try to enforce these things. But typically with sandboxing solutions, you're going to take some unmodified software or potentially untrusted software and then run it in a special environment to try to encapsulate this stuff. So why do you do sandboxing? Well, okay, so to help reduce the attack surface, because basically when if you run a program and you're running in an environment and it can access anything, then that's a very large attack surface. And so when you run in a sandbox, the attack surface is much smaller. And this is a principle called principle of least privilege, which basically for any task or process that you're using, you want to basically only give it the privileges that it actually needs, and don't give it other privileges, because those can be increase your attack surface and be vectors for attack. And so basically, you just want to restrict the possible actions that task can do to just be the ones that are actually permitted for it to do. And that's really what all the sandboxing technology does.
Yeah, I'll talk about this quote that I put up. So this is by a professor at UIC, I think, actually, Dan Bernstein, and so this is from his research statement. So he talks about the idea of you have a music decoder and you're taking some compressed music audio and you want to turn it into something uncompressed. You want to play it, for instance, or you want to turn it into raw music data. And so he says that the output is entrusted any more highly than the inputs. So what is the output? It's the uncompressed music audio, and what's the input is the compressed audio. And so if you run in a normal music player, you put some input in there, and then there's some memory vulnerabilities in this decoder, then now the output is not just the music that you're listening to, but it's also, now I can make system calls, now I can open files, now I can mess with things if I can exploit this program. And so the idea behind sandboxing is that you restrict everything to what it can do to just be to write to this existing handle it has to your audio card or to whatever file you're writing to. And so that's what they're saying. If that's all you can do when you can exploit it, you could just have given me a modified music file as input, and all you can do is control this output that you're already legitimately authorized to modify, which is the uncompressed music. Yeah. And so that's basically what sandboxing is. It's restricting, say there's this huge attack surface of this system call interface or file system interface, and we're going to restrict that to just be all the music reader needs to do is to output to your audio, to your speaker system.
Yeah, I mean, basically, you can't really increase the trust by having, having when the input comes in. I mean, whatever input that come in, however much you trust that is exactly how much you can trust what the effect and the outputs, possible outputs of that can be. And so, if you have a good sandbox, then it'll have this property.
So this is what we've been. This is a very generic definition of sandboxing, and we're not talking precisely about you're isolating a component that happens to be an app or a code that happens to be a kernel. It's just you might be sandboxing an entire kernel, you might be sandboxing an entire OS, you could be sandboxing just one thread in a process, but it's this same idea.
Yeah, and like the sandboxing is really, this is like a good practice of like engineering practice for designing systems that are secure, and then there's a lot of different places that you can actually apply this technique. So let's talk about some of the techniques. So we'll cover five techniques. And there's various products that use these techniques and what the pros and cons of each of them. There's a bunch of other techniques, but we're just going to cover 5 of them this time. First one is called master-slave sandboxing. So the basic idea with master-slave sandboxing is you have 2 processes. One is the sandbox process, that's the restricted one, and the other one is the regular process, the broker process. And then, so what happens is the sandbox process can't do anything. It can't access files. It can't go and open network connections. You basically restrict it completely. It cannot do anything except to tell this other process, I want to do this operation. And so then the other process then can take that request and then validate it. It can check, hey, is this guy? It can check arbitrary things like, hey, is this guy allowed to do this? Is it okay for him to write to this file, or is that not okay? Do I allow him access to the clipboard or not? You can implement arbitrary code in the broker process to check whatever you want. right? And then you use some inter-process communication mechanism, to communicate between this very restricted process and the broker process. And so the good thing about that is, even if you completely compromise that sandbox process, that sandbox process is completely compromised. You can run arbitrary code in there because it's running inside of the sandbox where it's enforced that the only thing it can do is to have this very narrow interface to go and talk via inter-process communication to this other process. Then, as long as that mechanism is secure, then you can improve your security, right? And so Adobe Reader uses this. So like Adobe Reader used to be like there's so many PDF vulnerabilities, and they eventually basically just got sick of it, and so they built this architecture so that the renderer is separate than the broker process. And so you have your renderer, which there are a ton of exploits that people found because the file format's really complicated and it's really hard to build something that doesn't have any bugs like this. And so they basically restrict that the ability to kind of read and write from that container, and everything all the API calls have to go through this broker process. Google Chrome does the same thing. So Google Chrome has a very nice sandbox. And on the Windows side, they use operating system features to basically drop all the privileges of what they call it the target process, but it's really the sandboxed process. And so they give it a restricted token where it can't access anything in the system. They use this job object, so it can't, other things on Windows, it'll isolate it. They use an alternative desktop, so other things like Windows hooks and stuff won't be injected in there. And then they on Vista and above, they lower the integrity level to basically low, which really restricts, which adds another level of restriction on what that process is allowed to do. So effectively, that process really can't do much of anything other than it can access fat file system volumes, because in Windows there's no restriction on accessing fat volumes, and there's a very short list of other things that it's actually allowed to do. And so all the other operations go through the broker. And so it has to basically tell the broker, and then the broker can then check to say, hey, is this sandbox allowed to do this? And when you run Chrome, if you ever run Process Explorer, you'll notice there's a whole bunch of Chrome processes there. And that's because they're all of those are every single tab is running in a separate sandbox. And so they do this for security, and that also makes Chrome one of the most secure browsers. Although, as we'll see, there's still ways to break out of it. So the second technique I'll talk about is a kernel level sandbox. So basically, this is either a kernel driver you install or a feature of the kernel that allows you to intercept all the system calls that happen, and then you can make checks at that time. It's hey, are these valid arguments? Is this person actually allowed to do this system call? And most of those Windows sandboxing process, the products, this is what they do. They do some variant of this, and this is what they're selling. One of those examples is on Unix.
So I guess we're first want to talk a little bit about service isolation. So without even modifying the kernel, there's some things you can do. In NT you can do most of these things, but these are just things that have been traditionally done on Unix. Every service runs as a separate user ID, and so I compromise my web server, can't write to the files of my SQL server or my mail server, whatever it is. Android actually takes this to a very nice extreme, which is, there's only one person who owns the phone. There's no need for Unix's multi-user facility on the phone. It's running a Linux kernel, so let's give every application its own account, essentially. And so now each app has its own home directory, each app has its own ability to debug, I guess, those sorts of interfaces within the app, but they cannot cross the app boundary. Unix has this thing called chroot, which says, I'm going to take this subdirectory inside the file system, I'm going to use that as my root of the file system now. And so if there are ways to break out of it, there are some vulnerabilities there, and so it's definitely not a perfect solution, but basically it says if I'm running an untrusted FTP server, which is exposed to the public internet, I say all you can get to is this subdirectory of my file system, you install a copy of the base things you need for the OS in there. And the services, there's a facility for saving your user ID. This is another type of sandboxing, and so this is where the application is trusted, but maybe you're taking in a file name or something that like you're passing in from a user. And so you save your privileges, you drop to something with lower privileges, you try to open the file, and then the kernel checks you against your lower privileges. Then you can now restore that existing user ID. And so if someone's giving you a file name and you have to save a file to like someone's home directory, you temporarily switch to them. And so this is not protecting against arbitrary code because obviously you can restore your saved ID, but it does protect against making sure that it uses the kernel's existing check for file names. So yeah. So system call restrictions, some of the things that, so there's some Windows products that add this on. There's some things in Linux and now iOS and Mac OS X's kernel. So Linux has a nice thing. I really like this because it's solid. And Chrome uses this, and it's actually been the Chrome developers in the last year or two who have taken this feature and run with it, called the secure computing mode. And so the original idea was someone wanted to build this, I guess what we'd now call a cloud computing service, probably a little before the days when that term was in vogue, where they said, you want to run some mathematical calculations, I'll run it on my servers and charge you for it, but you're now giving me programs to run, and so I need to trust what you're doing. And so what they do is they have this mode where they say you can make 4 system calls. You can read to an existing file, from an existing file descriptor, existing handle, you can write to an existing handle. If a signal handler comes, you can tell the kernel I'm done handling the signal, and you can quit the process. And that's all you can do, and like read and write are basically literally the oldest system calls in Linux. Those are well audited paths. If you're not passing the process handles to strange file systems or strange objects, you're just passing it like a pipe to another process. These are very well audited paths, and the secure computing stuff is right, it's nice. It's right when you make the system call. Before anything runs in the kernel, it just says, are you in secure computing mode? If so, are you running these calls? If not, you spent basically no time in the kernel before it kills your process. So that's very solid. I wish Windows would have something like that. So Chrome uses this to protect, you'll see a lot of real sandboxing products use multiple of these levels. So it uses that to protect its sandbox on Linux. Well, they're using actually now a little more extensive language based on the Berkeley packet filter, which is an existing language in a kernel for doing, if you're running Wireshark or something, you say, I'd like to capture certain packets that follow these rules. Well, it's the kernel interpreting that. So there's this existing language. So now I can say, well, I can read from this file descriptor provided I have these constraints. Or I can like run this system call provided this argument matches that argument. So this is a little more expansive, lets you do a few more things. And so this is that. So the Chrome developers have been running this recently and pushing this into the kernel. That's been fun. SELinux and AppArmor, you can call them sandboxing solutions. I definitely call AppArmor sandboxing. SELinux I wouldn't call sandboxing as a whole, but there have been some folks with Red Hat who have done sandboxing solutions based around it. And so this is taking a process and saying, it's similar to system call restrictions, although it's at it's a little later level, so it's not immediately when you make the call. It's checking objects and saying, do I have permissions to access these files? And so Ubuntu, for instance, runs a bunch of services on AppArmor by default. And so your DNS server is now saying, oh, all I can do is serve DNS. I can't go and write to people's home directories. There's this sandbox called Seatbelt, which is basically in the same vein on the Darwin kernel. Is what you use to sandbox iOS applications and what you use to sandbox Apple App Store applications on the Mac. So there are 2 modes for that. There's some predefined modes where you say, well, this process can't get to the network, for instance. And then there's also this language where you can specify custom profiles and say, oh, this system call can do this, or oh, you can read files that match this, but not files that match that. So the profiles written in Scheme, and they were, I don't know why they chose Scheme, but they were very clever and didn't put the Scheme parser in the kernel. So they parse this out, they run this program, and then they send the kernel, here's this minimal binary format for parsing these things. And so that reduces the attack surface. And actually, if you notice on iOS, every app runs as the username mobile. It's a Unix system underneath there. But the sandboxing scheme basically tells every user they've got a different home directory. And so every application, you've got a different home directory. So an application can't see the files of any other application. Again, there's always attack surface there, but that's pretty secure.
Yeah, and then in general, Linux and Unix-based ones, and then as well as the mobile OSs, they're much further ahead in these areas, of security, and then that's why all these Windows products are basically trying to add something, bolt on something like this to onto Windows. Yeah.
I really think that's because mobile's a newer landscape. Nobody has any legacy assumptions. Kind of what was being said yesterday about Windows' middleware and so forth. Moving away, we're starting this new platform. Android has the option to say, you've only got one user on the device. I know that. I'm not doing multi-user logons. I'm going to reuse this facility for separating apps. iOS has this amazing ability to say, you don't have a shared file system. Each app has their own files, but like there's no desktop, there's no My Documents on iOS. And so you can't get away with that on the desktop quite as easily. Apple's trying, Microsoft's trying, but that's why I think the mobile platforms are so much better, because they just started from scratch. They had lessons of 20 years to work on.
Yeah, and I think that the security record reflects that as well.
Yeah.
The third technique we'll talk about is dynamic recompilation. So we talked about we want to enforce that some checks happen before you do some system call, right? I mean, so you can put something in the kernel that's going to go and do those checks. You can do that, the master-slave thing. So like you have the Sandbox process try to, basically RPC to another process that does the checks. Another way to do it is you can just rewrite the code. So as you're executing the code, you see something that might be malicious, like a system call, and then you can basically disassemble that code, insert some checks, and then reassemble the code. And so this is, this technique was fairly common, like, back in the old days before there was hardware support for like VT and things like that. Because, if you go to like, remember the first versions of VMware, they do like binary translation. They're effectively doing something like this. There's certain sensitive operations that you want to do, like mess around with the page tables and stuff. And then so they needed to be able to have hooks in there. And the way they had hooks in there, because the CPU didn't give you the ability to trap there, is they would rewrite the code to basically insert those hooks. And so if you're smart about how you do this, then you can do this in a very secure way. So that it's a technique called program shepherding. There's Determina, which is a company that did this sandboxing security a long time ago back, and they got acquired by VMware. This is the technique that they use. Nowadays, not many things use this technique. I mean, some like in Java virtual machines where they have a dynamic compiler will do these kind of things. But it's nowadays, because you have support on the processor, you don't have to go to such extreme lengths to try to insert checks before calls. Binary verification. This is very cool. So one example of this is in Google Native Client. But basically what it is if I can take your binary code that you're going to run and I can somehow analyze it and then prove that this cannot do any of these malicious operations, and the way that Google Native Client works is basically you take your program and you run it through a special compiler such that the output binary code is like of a very particular form. So the form is such that it makes it very easy to verify that there's nothing funny going on. So like they do things that so when you have arbitrary binary code, you can do crazy stuff, like you can jump to a middle of an instruction and cause it to do weird things. You can call like unsafe instructions, you can generate code, you can jump around in various places. What they do is they basically, in the compiler, the compiler phase, they enforce these constraints that, okay, all the, when you jumps, you can only jump to some place like at the start of one of the blocks, and you can't jump to in the middle. And, and then they enforce a handful of other of these properties, and then they can then prove that this code cannot do anything malicious. So the downside of this is that basically this is not your arbitrary binary. This is basically you have to take your program and then recompile it for native client, and there's a small performance penalty because you have to the jumps are like longer instructions. All the instructions get longer. Various other things. And then they have a code verifier that basically ensures that this code can't do any unsafe operations. And then that code verifier is just like a small piece of code so people can look at it and say, there's no bugs in this verifier. Therefore, then this code cannot do anything malicious. And Google uses this, like if you go on Google Chrome and you go to websites and stuff, you can actually play like 3D games, and you can play like things which take a lot of processor power, and that's actually running on native code like x86 code, although it's compiled for native client, and so that's how they enforce this this boundary. And then the last one I'll talk about, the last technique, is basically operating system virtualization, or like a hypervisor. Basically, you contain the entire operating system and then you run on a hypervisor layer. So examples of this, I mean, if you have something like a VMware or a VirtualBox or something like that, or Zen or Hyper-V, Bromium uses something similar to this as well. Yeah, so those are the 5 top techniques, general techniques for doing these. One.
Can I toss in before we move there? Just to say, one thing we do on one of our products is you're on a bare metal hypervisor and you need to get a web browser because you're in a Captain Portal or something. Instead of sticking a web browser in our product, we say, oh, we'll just spin up a VM. The VM contains a web browser. You access whatever sites you need, you authenticate with the portal, then we kill the VM and wipe everything that has stayed inside it. So it's not very complicated, and we already have enough facilities to run VMs, but it's a form of sandboxing. You're just sandboxing the entire browser. You're also sandboxing the kernel that runs within the browser, and you're protecting all of that from the host, and the host remains trusted that you can browse to whatever you want.
Yeah, and ultimately, things like that, when it reduces the attack surface, right? So instead of having to protect, instead of having to make sure there's no bugs in the entire Windows kernel, all you have to do is make sure there's no bugs that allow you to break out of through the hypercall interface. And the hypercall interface is much smaller. Maybe that's like 30 calls, and it's a lot easier to check that than the 500 calls that would be on the for a Windows Windows kernel interface, right? So anyway, those are the general techniques of sandboxing. One thing to realize is that no actual sandbox is fully secure.
100% secure.
Is 100% secure. Because number one, all sandboxes they all have software components, and like whether you call it, whether that software is in a hypervisor or that software is in an operating system, or it's the checking code to verify the policies. Software written by humans, it always has bugs. And like a correlate to this as well is like, even when you think about, well, what about hardware? I mean, hardware will protect you, right? Well, if you actually look at hardware, like you look at how does Intel make VT, and how do these chip makers make these? Well, they have a bunch of microcode that was written by people who are basically designing this and writing this. And sure, like Intel spends a lot more time and a lot more effort to try to make sure that the stuff they do is correct, because it's quite expensive if they screw up. I mean, they have to push out microcode updates, and it's embarrassing for them and everything. But all of these are still, this is all still software written by humans that has bugs. And there have been and are bugs in hardware implementations as well that allow you to break out. And there's lots of examples of those.
I just reinstalled my netbook remember netbooks from 2008, I guess?
Yeah.
So I reinstalled that with the latest version of Debian. I booted up and it says, microcode update required. We're going to disable the ability to do something or the other to your page tables, because it's an Intel Atom processor from 5 years ago. And hey, there were bugs in the microcode, and Linux is going to disable some features for me because it says there's no way to use it securely.
Yep. Second thing is that when you think about a sandbox, right? You are trading off one attack surface for a different attack surface, right? So when I first run my process normally, my attack surface is whatever operating system and other things it's interfacing with. And so now if I run that in a sandbox, I basically have replaced that one attack surface with a different attack surface, which is either the RPC mechanism or the hypercall mechanism, or one of those things. And so it's not like, oh, it's in a sandbox and now it's now it's secure. It's just you're just replacing one with the other. And so you have to look at actually how secure is the Sandbox API to figure out like how much security you're actually getting. And sometimes you actually lose security. Sometimes you basically do a sandbox and the sandbox is less secure, and then you're not actually gaining anything, right? And you actually lose, right? So I mean, if you're doing this operating system level, well, I mean, like the kernel API. The kernel API is your attack surface, right?
That's your biggest attack surface on like Chrome on Windows, because you can still make system calls. The operating system is supposed to unprivilege everything you're doing, but if there's some Windows system call that has a bug in parsing its arguments, the sandbox process can escape from there.
That's right, yeah. And then kernel sandboxing, if you're doing it at that level, well then all the system call entries, right?
There was a fun bug, let me mention this. There was a fun bug in so remember I was mentioning the secure computing mode, where you make a system call and the first thing it does when you make that system call, once it gets out of like parsing that interrupt vector, is moves to C code. The very first line of code is if secure computing. So you're checking these system call numbers, you're checking read, write, so return, exit. You're checking for one of these 4 system call numbers. So when Linux added AMD 64-bit support for AMD 64 or x86 64, it's a new architecture, their system call numbers are different, and they said, well, we want to be compatible with running 32-bit programs. So they have this interface where you're running a 64-bit Linux kernel, and you can run both 32 and 64-bit processes on them. And the 32-bit system call numbers and the 64-bit system call numbers, those are not the same because, I don't know why they're not the same, but they're just not. They're just different lists. And so you're in a 64-bit process, and you're in secure computing mode, and you make a 32-bit system call using the 32-bit system call entry point, like int 80 or something, as opposed to the 64-bit system call instruction. And you set up your stack as if you're 32-bit. And you make this call, and the kernel's like, oh, it's one of these 4 system calls that's checking against the 32-bit list. But you're actually a 64-bit process, something like that. Just guessing wrong. And it's just like, now you can make the system call, which is just whatever happened to share this number. And that turned out to be something that gives you some amount of access to the system that they didn't want you to have.
Yeah,
So
I mean,
always subtle things like that.
Yeah, the basic thing is that, I mean, even no matter, like, you try to make it as simple as possible, that sandbox, to make sure that you implement it securely, but it's in real life is really hard, and like you can have these bugs and not even realize it, and it's really easy to have these bugs, and there's there's lots of examples of these bugs as well. Virtual machine, well, I mean, okay, well, if you have a virtual machine, there's still an interface. There is a hypercall interface. And device emulation as well, because you're in a VM, you need to be able to access devices. And like that, most of the bugs in this virtualization, when you have like VMMs like Zen or KVM or VMware or Hyper-V, any of these, most of the bugs are in the device emulation part. When it's trying to emulate devices, because that's actually, it's a more complicated thing to do. So there's plenty of bugs and exploits in those. If you have the master and slave processes, RPC parsers, so you're making a remote procedure call, and like those remote procedure calls that you're doing, I mean, it's not like you make that call, you also have to pass some arguments, and the arguments may be something complicated like a tree or a other type of data structure. And then you have to parse that in, and then there are plenty of cases where you don't do that exactly right, and then there's an exploit, like a integer underflow or all those kind of attacks, right? And There's like basically any sandboxing technique that you have, whether it's in hardware or software, any of these, pretty much there will always be some type of exploits that you can do against it.
So I'll believe you if you tell me your sandbox solution, you'd stop 100% of existing attacks against this existing attack surface. But your sandbox solution is introducing a new surface, hopefully a smaller surface. Some of the ones I really like native client, have a very tiny new attack surface. That's why they're well designed. But you're still introducing some new surface for attacks. And what sort of new exploits can you make against the new attack surface?
Yeah. Oh yeah, so there's this quote, this is a guy from Gartner, but basically this kind of sums up, even the strongest prison needs doors in order to be useful, and the same doors can be used to escape. And so this is, when you're talking about these secure sandboxing, ultimately to make it have a useful sandbox, you need some way in and out, and those are often good paths to be able to escape. So let's go through some examples of how people have exploited sandboxes in the past, and then you can kind of get a gist of like what type of attacks people can do. And so when you have a sandbox solutions, what type of things you can be protected against versus not. Google Chrome Sandbox. So Google Chrome does something very cool. So all of their stuff is open source, and they have these competitions like the Onium, like the competition, where they will pay like cash to people who find exploits, basically ways to break out of the sandbox. And so there's this one kid he's like 17 years old. He goes by alias Pinkie Pie, and he's made like $160,000 in like 1 year from Google just by basically finding a couple of exploits and then basically doing it at this competition. But this is actually really great because then the process is very open. It's all open source. They can find the bugs. They can fix them, and then if you put up a $2 million bounty, and then it's a pretty good incentive. Now, to be fair, like if you took one of these Chrome exploits and you sold it on the black market, you could probably get a lot more than $100,000, like for a 0-day like Chrome sandbox exploit. But but still, I mean, like they have this process, and they've been doing this over time, and they've had these events. So let's go through like just an example of one exploit like that Pinkie Pie found that actually will allow him to break out of this Chrome sandbox on Windows. So it was actually a chain of 6 different bugs/exploits. And so this is something you'll see often with sandbox solutions, because basically sandboxing, it's virtualization to add isolation. And so once you kind of break out of one level of the sandbox, you then need another exploit to break out of the next level. And so in this case, he actually just chained 6 different exploits to finally get out of the sandbox. So first of all, there's the first bug was there's a feature in Google Chrome to do pre-rendering. So basically, when you go to a web page, you want to render it before it actually shows to make it for good performance, right? And there was a bug in there that will allow you to load a native client module, which you normally would not be able to do from one of these tabs. And then in native client, basically, native client allows you to do GPU operations because you want to be able to do like accelerated graphics inside of your native client program. And so he used the native client to generate a GPU command buffer that had an integer underflow bug. So integer underflow, basically, when it's calculating the size of something, they subtract something and then it ends up wrapping around to be like a huge number. Like, so they go like below 0, and then it kind of wraps around to become a negative number, which looks like a huge number. And then they eventually be able to use this, and they're able to overwrite 8 bytes in the process space, in that process space. And they overwrite, and this they can actually decide, there's address space randomization, so layout randomization, but they're able to basically figure out, here, I'm going to overwrite these particular 8 bytes, and they overwrite it in the GPU bucket tree. And so, like for when it's doing the GPU operations, it has this data structure to do that. And then there is, so they overwrite that in the bucket tree, and then they utilize a race in the named pipe setup from the GPU process so they can impersonate the renderer in that process. And then they use another bug to chain that to another bug, because there's a bug in the render that will trigger you to navigate to a privileged render from because the renderer itself is sandbox, so you can't really do much from the renderer, to a privileged renderer, and then impersonate the extensions manager. So if you go into Google, there's like an extensions manager thing. So that has like its own renderer, which has slightly different permissions. And so then they figure out a way to exploit that and then impersonate the extensions manager. And once you're in the extensions manager, you can then the extension manager is allowed to actually load extensions, but not from the renderer. So the renderer is against Sandbox. And so he found a bug in the extension manager to allow you to load the extension from the renderer instead of the normal extension manager. So I did that. And then finally, he found a bug where in the extension loading that would not prompt the user before it tried to load one of these legacy extensions. And so if it was an unpacked extension, like they forgot to put the code that asked the user, hey, this is unsafe, do you or should you want to do this? So basically, he was able to chain like all 6 of these bugs, to eventually, so you can just go to a web page and then your system, your Windows system gets owned. And that's, and so he was able to demonstrate that. And I think like a lot of times, like when you look at these things that are protected by sandboxes, like a single exploit usually doesn't do it. Like you often have to chain these exploits because as you break out of each progressive level of the sandbox, you have to do those kind of things.
Yeah, if you're doing a security review of your product, somebody constructs this scenario where you're like, oh, you can get out of this, and then go to that, and go to that, and like your answer is, oh, but nobody's ever going to do that. 17-year-old kids on the white hat market are doing this. Someone who's a black hat who actually wants to get to some interesting corporate data and doesn't just want, fame and glory and $100,000. They want millions, millions, and millions of dollars and are full-time and are experiencing this stuff. They're going to do this. If you've jailbroken your iPhone, go look at how complex that exploit is. There's like 10 things they chain to like go from the USB to like the breakout of the sandbox of the application, to get a persistent untethered jailbreak, to do this, to do that, to do that, and then finally jailbreak. Look at how complex those things are, and people do that, and that's the stuff that's public.
Yeah. You want to talk about this one?
So one of the things about the attack, in terms of attack surface, just note that Zen has, of course, a hypervisor, and we talk about the hypervisor as the trusted code base. The same argument basically applies to many other virtualization systems. We talk about the hypervisor as the trusted code base, but there's also the domain 0, the dom 0, which is trusted to tell the hypervisor, do this, do that, run these drivers, emulate this. And if you can get root in the domain 0, you can get root. You can do whatever you want to any of the guest VMs. You can basically, you win.
Yeah.
And so there's all of this, essentially legacy support for the PC platform, this whatever IBM came up within the 80s, that ever since then, every OS has been, certainly Windows, has been expecting all of these things to work. And so you're running Windows inside Zen, you have all this device emulation. So this graphic is taken up from some folks who basically concluded there was no good way to reduce the size of a trusted code base. And so they said, we're just going to split it up as a research project. We're going to split it up and just reboot all of the components we can reboot as like micro domains as often as we can in the hope that we'll like reboot it before anything happens. And they just, paper title, breaking up is hard to do, and they couldn't come with anything better. So a couple of exploits. There are a bunch of exploits in Zen, but I just want to talk about this to get a sense of, to give a sense of what it takes to or what the trusted code base is and what it encompasses. So a friend of mine found this one, presented at Black Hat a couple years ago. Basically, there's the clock, the device, the hardware clock, which is emulated on Zen. And you can tell the PCI ISA bridge to hot unplug itself, like it was a card, but it's not a card, it's a bridge. And this is not doesn't really make a lot of sense to do that, but the QEMU process, which is what does device emulation on KVM and also does device emulation on Zen, will happily go and just free this memory. So now you have freed memory, and now you have timer interrupts that are just firing, and the way that it emulates is it does a function call into this memory, and this is what you've just freed. And so you need to find a way to control that. All you need to do is deliver a network packet to the VM. Contains anything you want. It's going to be allocated into the memory that was just freed. And so now, next timer interrupt fires, it just calls in on the host side into this timer interrupt. Yeah. There were a bunch of other things to make that exploit work, but this was the big one. So this one's also fun. This is not a host escalation, but just to get an idea of what this code base looks like. When you were doing DMA, I forget if it was DMA for Ethernet packets, the operating system asked the driver, hey, give me 50 bytes from the next packet. Or give me, I guess, 1,000 bytes, something reasonably sized for a net packet. And the driver just doesn't check how many bytes the OS asks for. It says, I've got 5,000 bytes. I'm just going to write them there, whether or not you have room for it or not. And so it's very easy, if you're running this particular, I think it was the E1000 Ethernet card and emulation, just send the jumbo Ethernet frame, and we'll go and start overriding things in the guest kernel, and that's an easy guest root. This one was also just fun because of, just think about the fact that this code exists and how little love it gets. They're doing console emulation for your serial port, and they have a VT100 emulator, and you've got these VT100 escape sequences, and you have a sufficiently long escape sequence, and the parser there just buffer overflows into host memory. And so all of this is running inside, essentially, the trusted code base. I mentioned my friend presented the first one, 2011 1751 Black Hat. His paper has the quote, "a veritable goldmine of targets," is his phrase to describe what this device emulation stuff looks like. And if you're running Windows, if you're not running something custom, if you're running like Linux on AWS, they're generally running this paravert, so they're somewhat better off. If you're running legacy Windows on a hypervisor, you've got to emulate all of these devices.
Yeah. Yeah. So So basically, I mean, like when you're talking about the virtual machine, and you say it has a narrow interface, it still has a very wide interface for device drivers and everything, and emulating these, and they're very complicated, and there's tons of bugs that they found. There's tons more bugs that exist, and that allows you to break out. So, that's and that's kind of the basic idea is like the more complicated the code there, and the more buggy that code is. Yeah. The more exploits that you're going to have, right?
So there's some other fun things. If you think that, for instance, I'm sandboxing, let's say I'm sandboxing a browser process, and I'm going to allow the browser process just to access the untrusted internet. I'm not going to let it access any domain names on my corporate website. I'm not going to allow it to access anything high value. There's a thing called a DNS rebinding attack. It's actually a known attack, and there aren't very many good defenses against it. Well-written websites should have defenses, but you have a JavaScript running on attacker.com, and it does an XML HTTP request to data.attacker.com. And data.attacker.com, they have now repointed that DNS address instead of something they control to, like, I don't know, your internal version control server, 10.0. something. And they do an XML HTTP request. It's the same domain as far as the browser knows. And your internal server is probably just exposing, like you've almost all got an internal wiki on your corporate network, and it's just exposing stuff to people who happen to be on the corporate LAN. And now this browser, this JavaScript code from an external site can just do a XML to HTTP request, snarf down that data, upload it back to wherever it's going to, if they can guess your IPs right, if they can.
Yeah. So I mean, I guess the point is you can have a perfect sandbox. You have an absolutely perfect sandbox, and you can say, you know what, everything from Facebook.com, that's all going to be run within this sandbox. And then, but using something like this where it's like, well, okay, star.facebook.com, fine, that's going to go in the sandbox, and that can go and do whatever we want, but it can't access the rest of the system. Well, what you could do is just hijack DNS and say, whatever, a.facebook.com points to my internal server with all my secret stuff on it. And then you can use the little JavaScript, which is fine to run, and then that untrusted code can just, that's running in your untrusted partition can go and access, various parts of your, internal network and stuff. And so these type of attacks are very hard to prevent against because, you either restrict the functionality or you open yourself up to attacks like this.
Right, because this is not a sandboxing failure. This is not sandboxing's job to solve. It should not be the problem of your sandbox to determine whether web security standards are up to snuff. But this is going to be a problem. And you can't say, well, I have a sandbox around it, so I don't have to worry about it. Yeah. Relatedly, a lot of the malware that you have on systems is not interested per se in attacking your corporate data. It's just interested in using you as a platform to launch more attacks. It wants to send spam. It wants to launch coordinated DDoSs against site. It wants to do command and control for botnets. It wants to infect other PCs on the network. And so you say, well, I'll let my untrusted sandbox browser have access to the public internet. And now all of a sudden, all of your machines on the public internet, and you say, well, I've been sandboxed, I'm safe. And all of your machines that have access to the public internet are now launching DDoS attacks against other companies. Now they call you up and say, hey, stop, cut that out. And you say, I sandboxed it, what's going wrong? So.
Yeah, I mean, I guess the basic point is, I mean, even when you do contain stuff purely within a sandbox, there's still plenty of bad, and you have a perfect sandbox and it doesn't break out of that sandbox.
Yeah, it's not getting into your host computer.
Yeah, it doesn't get into your host computer, but there's still plenty of bad stuff can happen. I mean, they can basically DDoS other people. They can put you on spam lists because now you are distributing spam and from your corporate network and cause all sorts of problems, even if they don't break out. So.
And so this, you could say this could be within sandboxing's purview if you start defining tighter and tighter policies, like, oh, DNS can't resolve to within my corporate network's IP space. Oh, but what about external sites? Oh, I can't talk to spam servers on port 25. What ports can you talk to? And so now it's just a mess of policies, and you have to start to guess what sort of behaviors are and aren't authorized.
Yeah, and so there's a whole set of attacks which are called side channel attacks, which is not a direct attack against the sandbox, but you can discover things about the sandbox or other type of execution just by happening to be on the same machine. So there's a whole set of things like memory cache timing, where because I have a sandbox that's totally secure running on some machine, and other stuff is also running on that machine. I can look at what's in cache. I can figure out what data people are accessing. There's been a whole bunch of timing attacks on crypto. So like one VM or one of these sandbox things is doing crypto operations. The other one is running on the same machine. You can measure like very precise timing and then figure out what the keys are on the other side on the crypto. Things like DNS query cache, like this is a good example, right? So you want to figure out like you're on the same machine as somebody, and there's a shared DNS cache there. You want to you have like you want to figure out if somebody else on your in one of those sandboxes is accessing some crazy website like crazyhorseporn.com or something, and and you want to figure it out, and you do a DNS query. And it's like it comes back immediately. It came back from the cache. It's like, huh, okay, I guess somebody else on this machine is looking at that website, right? And these are the things that Sandboxing doesn't really help you with. I mean, there's there's other type of caching, the file system block device cache stuff. When you're doing deduplication, and you can figure out like other people, do other people using the same blocks, and then you can do these type of attacks. This one's very cool.
Interrupt timing is pretty great. So you're running on a same processor as something else, and you can keep track of the real-time clock, because that's not a thing that the sandbox is going to stop you from doing. That's just a processor instruction. And so you record when you're running and when you're not. And so you say, well, my keystrokes aren't going to sandbox, they're going to the host partition. You can't watch me type passwords. But when I hit that keystroke, it causes an interrupt. It goes to the host partition, and then it returns me back to the sandbox. And so you say, okay, so I know when you hit those keys. There's been a large body of research that says if you know the timings when people hit their keystrokes, that's very strongly correlated with what keys they're typing. With, I'm going to type two keys that are next to each other or on opposite hands way quicker than I'm going to type two keys I need the same hand that are far away from each other. And you can learn these things. You can basically guess their passwords if you've got those timing data right.
Yeah, and so there's a whole class of these type of attacks that basically sandbox. This is like outside of the purview of sandboxing. And even if you have a perfect sandbox, you can't do anything about any of these. And so, I mean, and there's some challenges in implementing sandboxing as well. I mean, we talked about a perfect sandbox. It's very hard to implement a perfect sandbox. Basically, you have these problems. There's this like, tuck-toe.
Time of check to time of use.
Yeah, time of check to time of use. So like, let's say you check the arguments or something, and so yep, it's good, but then you use it sometime later, then you have to be really careful about those type of timing bugs, because in the meantime, they could have used it was like, yep, you're verified, and then you swap out the arguments, you swap the, it's like you went through if you go through the airport security, and you put your bag through, and then basically, I was like, oh, yep, bag is good, and then somebody swaps the bag with an identical looking bag, at that point, and then you can just keep going, and it's like, oh yeah, that's fine. The other interesting thing is a lot of times you can have a single, you have a sequence of operations, and you can verify, yep, every single one of these operations is good, but when you combine them all together, then they could end up doing something bad. And so this kind of stuff is really hard to find and make sure that you're not doing.
There was a large class of attacks, at least in the academic space, and so I have no idea if this is true of current Sandbox products for Windows, but I wouldn't be surprised if it is, where you check these system call arguments, and they're pointers into user space memory, and so you can only check them right when your thing runs. But this user space memory is actually like a file that's been mapped from disk. And so after your Sandbox product verifies it's good, somebody else modifies the file on disk, and the kernel then goes and reads that memory later.
Yeah. So there's also, there's also been a set of like hardware bugs, or I mean, so there's been problems in like the implementation of hardware. So one example, so Intel, they have this basically privilege escalation vulnerability that allows you to break out of Zen, allows you to break out of Microsoft, basically it was very cross-platform. And what happened was Intel had implemented like this sysret instruction in a weird way that it had the semantics of it were not not really like they basically allowed you to break out and AMD basically got it right and like Intel basically got it wrong.
They implemented it in a way that was different from how AMD implemented it and did not strike anyone who was writing OS as well, maybe except folks who are reading the manual very carefully as the way that they would have. It was all documented that this is how they did, but everyone just assumed, oh, AMD and Intel implement the same instruction the same way.
Yes, and this was an example, and this was, look, you can now break out of Zen or like a number of these other hypervisors. And I mean, so Intel said officially this is not a bug because it matched the spec, but the spec was just stupid, and then the spec didn't match AMD, and and then so they ended up with this.
Because there are very few people who are writing operating systems, right?
Yeah.
Like there's Windows, there's Linux, there's VMware, there's Zen, and how many other people are just paying full-time attention to the minutiae of the Intel and AMD specs and getting all those details right, and that they're complicated specs.
Yeah. I mean, the other point is like basically what code are you actually running? You say, oh, I installed this Sandbox product on my computer, and so obviously I'm secure, right? I mean, I see the icon, it pops up, and it says like I'm secure, I must be secure. Well, the question is like, what code are you actually running? You don't actually know what code that you're running, especially unless you have something like a secure boot or like integrity measurement and basically track this all the way from some secure root. And so this is like if somebody had if somebody does find out an exploit, they can very easily persist it by replacing anything in your early boot, and now everything else after that cannot be trusted. Or I mean, if you take your compromised Internet Explorer and you use it to download Chrome, it doesn't that doesn't matter, because then the compromised Internet Explorer can basically download a malicious Chrome that like doesn't do sandboxing. So I mean, you have to be careful about what code are you actually running, and do you actually know what code that you're running? And there's these techniques like secure boot and things like that, which will help you attest like what code that you're actually running. So one interesting thing about this, so like when I first was doing this, preparing this presentation, my plan was to actually go and like evaluate, like basically show you demos of the various products. And so I contacted the various vendors, and the responses I got were either completely ignored, or like an explicitly do not talk about my product, do not demo my product, do not under any circumstances do anything with my product because because you're not authorized to do it. I was like, oh, okay, I'm not even like, I don't work for a competitor to any of these guys. I'm not like, I'm just like basically researcher just like interested in this general topic, right? And this didn't bring to the importance of things like, so I obey their, I'm not going to basically break their, demo it anyway, when they explicitly said, do not demo this. And do not talk about it. I think the truth is that they're really worried about, because they know, all the vendors know that there are holes in their products. All of them know. I mean, and they do not want anybody, they don't want people to point that out. And, they're afraid that, if they release the product, publicly or, allow people to go and hack on it, people are going to find holes. And people are going to find, because there are holes. I mean, that's just the way it is. And so a lot of vendors will basically do, their thing against that is secrecy, not like opposite of transparency. They don't allow independent reviews. Like the only reviews they allow are ones that they pay for. So you'd see like some of this stuff, like basically some vendors have this certification where it's like, oh, I certify that I protected against all of these known vulnerabilities, and I paid the firm to do that certification for me. It's like that certification is not worth anything because you can do that. You can check all the signatures of all the vulnerabilities. And they try to do some stuff like, oh, we had some smart people who tried to hack into it and they didn't find anything. Like unless you do this publicly, like then it's basically not even worth the web page that that it's printed on. So the importance of things like an independent review, allowing independent reviewers to, open source helps a lot. The more people who view the code and are looking for all vulnerabilities, things like public disclosure, when they do have a vulnerability, they publicly disclose it, and then how often they're patching stuff. These are all important things to, in terms of transparency and security, because these things are really, really hard to implement correctly. And if you're not transparent about these things, then probably they're not implemented correctly, and there probably are bugs.
It also kind of goes back to the thing earlier about the attack surfaces. And you've got the sandboxing product can totally lock you down, in theory. Let's say we're using something very solid like secure computing, can totally lock you down from the attack surface that exists, which is your Windows kernel or the API to the web or whatever it is. But they're introducing something new. They're always going to be introducing a broker process or an RPC or a verifier or an additional bit of code that sits there to verify what you're doing and make decisions, a policy layer. Those things are now your new attack surface. And that has to be, you have to be able to evaluate those, or we're going to say, well, yes, we can stop all 100% of attacks that people wrote up to yesterday. But now that you've introduced your new software, what vulnerabilities does your new attack surface have?
Yeah, and some of these guys do it well. I have to give props up to Chrome for example, because they do all of the open source, independent review. They put up bounties for it. It's been around for a while.
They publish. They just get everything right, basically.
Yeah. So
they've had holes. To be clear, they've had holes, but they've been very public, and they do keep those holes quiet until they're ready to push them out to their users. But they're very public about, here's our source, anyone can look at it, anyone can tell us that we've got this tiny verifier wrong. And they've got it wrong, but.
Yeah, and so when you're evaluating this sandbox security, it goes beyond, so certifications, especially ones that are paid for, are not really worth very much. We'll look at, things like how mature is the code, how much has been tested, how much has been used, how much has been analyzed, and the more that it's true, the better off it is. So even if you have a brand new product that's all new code, there are bugs in it, there will be bugs in it. As well. And then it's not just about lines of code either. You could have a very small amount of lines of code that is completely buggy, or you can have a large amount of code that is, very, very, very secure. Like things like all the microcode in Intel, the Intel processors is actually very secure because they've spent a lot of time on it and to check the security of it. Large number of lines of code, but and so that it's not a direct, it's a very simplistic argument to say less lines of code equals more secure. The other thing is perfect sandbox is honestly not very useful because once you sandbox things perfectly, it breaks all the integration between these components. And then so what you have to do to make it actually useful, you have to build a model of what is this component actually allowed to do. And building a perfect model of what an app or a task is allowed to do is really hard. And many times it's just unrealistic. You cannot realistically build a model of what an app is actually allowed to do. And so, yeah, you can, so you can either go in two directions. You can lock it down, in which case you break the application, or you can, let more stuff go, in which case you have security holes.
If you've ever tried to run a machine, I'm sure some people are doing this in production, doing a fantastic job at this, but if you ever downloaded a Linux distro that has SE Linux enabled out of the box, and you have some problems with it, and you go and you search for it, the #1 suggestion on Google is just disable SE Linux. It's impossible to get all the policies right.
Yeah.
Okay, so this is a picture I found on the web of a kitty coop, which is this old product for locking your kid in something that looks disturbingly like a coffin, in the hope that he can't go out, can't throw toys out, pets and older children can't hurt him. He's safe, and you know it, even if you are out of sight.
Yes. So having a perfect sandbox, you can lock your kid up in a coffin, and then be great, right? Again, Sandbox only protects against certain types of attacks. You lose your laptop, no. You still, it needs to be encrypted. There's plenty of good state within the sandbox to exploit. You have sensitive information inside your sandbox. as well, even if you're sandboxing browser, things like that. And of course, like what you can do, you're in your sandbox, you can pop up the UI, you can ask the user, and the user will happily supply whatever sensitive information you want. And there's nothing you can really do about this with a sandbox, right? And sandbox doesn't protect you against these kind of things, right? In terms of performance overhead, there's a lot of argument, well, sandboxing has no performance overhead, 0. I've heard 0. This is the quotes from some of the vendors. Truth is, it has overhead. It's like virtualization. You slow down all the system calls, you have extra context switching, copy on write memory. You're using a lot more memory if you're using this copy on write techniques. Start running out of TLB entries because if you're using these virtual pages. So you can do a really simple implementation, which has a large overhead, but then of course you want to optimize it. And then to make it high performance is really complicated, and guess what? You just introduced a bunch more security bugs. So.
That's why secure computing has the 2 modes, because the first thing they did was we'll allow these 2 system calls, the plain old, unmodified, unaccelerated read and write, and then exit and say return. And then Chrome says, well, we can do that, but that's not fast enough. We want to do this. We want to do that. Let's do this, this, this. And now they're trying. And now there's a much more complex implementation right there, and so that's just a huge attack surface.
Yeah, so I'm not going to talk a little about the future of sandboxing, because this is, so don't get me wrong, like sandboxing is a great technique. It is a great technique for security, and I think it's one of the next innovations in security, and there's going to be a lot of products that are going to start to use these sandboxing techniques to improve their security. But there are limitations to it. So to improve the security, like to basically, rather than just have a bunch of random code on your trusted side, you could either do things like with proof carrying code or provably correct code, where you can now mathematically prove that this small piece of code is correct, that there's no bugs in it, and so that increases, and then at that point, as long as you don't have hardware bugs, then you're
to be honest, if your reaction to proof carrying code is this is some academic mumbo jumbo. Native client is honestly proof carrying code. The proof it carries is, I'm only jumping within this native client binary. I'm not making system calls, and that's all statically verifiable. And its proof is just the layout it has, and that's in use today. That's in use on Chrome plugins today. That's a real product, and so it doesn't need to be very complicated.
Yeah, and in terms of platform support, today, iOS already has this, Android already has this, the forms of this built in. OS X is starting to do this and pretty soon everything in OS X has to be through the Mac App Store. That's the way they're going. Windows is going to put this in their platform as well. That's just a direction. And then beyond sandboxing, there's a lot of limitations of sandboxing. The next generation stuff is something called undo computing, which basically you keep track of the provenance of everything that happened, and then you're allowed to roll back individual malicious actions without affecting the rest of the state. And so this is great for stuff like databases where sandboxing is not going to help you, and you need more fine-grained control of these things. And this is something that's still in the research world right now, but there's going to be actual products doing these things in the next few years. Yeah. So in conclusion, sandboxing is a very important security feature. It's just like ASLR, the outer space randomization, and DEP, but it's along the same class of those. It helps you protect against some current exploits. There will be exploits that would still be able to break out the sandbox. There's tons of caveats to using Sandbox. It's not a security panacea. It's great for some things, doesn't solve everything. And don't trust Sandbox software that's not available publicly or doesn't work with security researchers, because then it's really hard to implement one of these correctly. And if you're basically trying to hide stuff, then you're probably doing it. You probably don't have it right. So anyway, yeah. Any questions? I guess we have a couple more minutes left.
Like 5 minutes.
5 minutes left? OK. Questions about sandboxing or anything else? Anyway, thanks everybody for sticking around for the last session, because I know that I know that it's hard to go to the traffic's going to get bad and stuff when you go back to the airport. So thanks a lot for everyone for sticking around. I remember, I know there's just like a dozen or so you here that so last year, one of the last speakers, he did a session and there was like 8 people in the session. And then so he got they did the speaker evaluation forums and he got like all 5s. And so he got the highest rated session because he had like 8 people who all rated him 5. So yeah, I'm hoping for a bunch of 5 so we can get a good session review and end up at the top of the session reviews. But anyway, yeah, if you guys have any questions, yeah, thanks a lot for coming, and yeah, hope to see you next BriForum.